turn off the machine, turn it on again, and the same nonces are going to be generated by all the servers. It's kind of that bad. So that is good for the attack because you can reuse all the dictionary that you have, that you will see in the demo that you can obtain that dictionary in, I don't know, 2 minutes, and then you can reuse that as if you have the password over and over again and with different machines, with the same machines all the time. And now, Agustin is going to explain to you how the third attack, that is a different vulnerability or a different flaw that we publish inside this vulnerability report, that actually exploits the fact that we can predict the challenges or nonces that the server is going to generate. In order to do that, you need to understand the whole mechanism that the server uses to create these nonces. And Agustin is going to explain as better as we can that, because it's kind of complex, so bear with us.
Hi again. Well, once a server receives an authentication request, it will call the function getEncryption_key to generate a challenge or an encryption key as it is described in protocols. So I will explain the getEncryption_key function. First, well, the getEncryption_key function is inside the srb.sys module. And the first thing it will do is retrieve the current system time using kernel query system time and create a seed. We'll create a seed with a part of that time and also using a counter, which is called encryption key count. Then, once the seed is created, we'll call the RTL random function, which is a PRNG. And with that, we'll create a challenge and return the challenge to its caller as a function. So this is the getEncryption pseudocode that we arrived after disassembling the getEncryption_key function. The first thing we see is how it calls the query system time function. With the low part of the return value current time, we'll add a counter and we'll update that counter. And we'll create a seed using that formula. We'll only use the low part of the current time and only the middle 16 bits. And we'll add and subtract a number. And once the seed is created, we'll call the RTL random function 3 times in a row. The first time, we'll use the created seed, and the second and the first time, we'll use some kind of feedback that the RTL random function returns also. With the 3 numbers returned by RTL random function, based on the third one, we'll modify the first and the second number, and we'll concatenate the results and return a challenge. That will be the challenge. So we know that the getEncryption key function gets entropy from the current system time and also from the counter. We'll create that seed, we'll call RTL random, and we'll return a challenge. So if we know the internal state of RTL random function and the current system time and also the value of the encryption key count, we can calculate all the numbers returned by RTL random function, and we can predict the challenge to be issued in the future. So I will explain the RTL random function in detail. Well, first, the RTL random function is a PRNG, which appears to be a Maclaurin-Marsaglia system that I will explain later, which uses 2 LCGs that I will explain later. So first, we'll create numbers using 2 LCGs as an M&M system. We'll fetch a value from an internal vector. The internal vector, it is related to the M&M system. We'll store a value into that vector, and we'll return the previously fetched value from the vector and a context to its caller. So I said that an M&M system uses 2 LCGs. LCGs are linear congruence generators. These functions are good for statistical randomness and for simulation, but it's not suitable for cryptographic purposes because it generates a predictable sequence of numbers. Well, M&M is the form of the RTL function. That's the algorithm for creating the sequence of number. It was proposed around 1956. And the authors wanted to improve the randomness in statistical means of the LCGs. In the paper that they are proposing that, they are also proposing using a table of known random numbers because they need the properties of random numbers, but they are not dealing with prediction or predictable sequence in the future. They are dealing with long periods of random numbers. So the basic algorithm is first create two numbers using the LCGs, construct an index to use it in the internal vector, fetch a value that I will call set, and store a value, and will return the previously fetched value. Well, I have like a little demo of what's happening inside there. We have the vector with n size length, which is initialized. First, we'll call the first LCG, then the second LCG. Based on the output of the second LCG, we'll create an index to use it to address values in the table. We'll fetch a value at the index created, and we'll store a new value, which was created with the first LCG, and return the previously fetched value. So again, a pseudocode of the RTL random in this case that we disassemble. We have, well, the context that it needs for the LCGs. First, we can see the formula of the LCG. It doesn't matter right now what's happening right there, but that's a formula of an LCG. That's the second LCG, so we have two numbers created. The second number will be returned as a context. Then an index will be created, and that index will be used first to fetch a value, and then to store a value, and will return the previously fetched value, and also the context. So we know that RTL random is an M&M system, so we can define two operations. A fetch operation that is dependent on the value of the table and also the seed, and a store, which is only dependent on the seed, but isn't independent of the values of the table. So we're trying to know what's happening between the different factors. First, what happens with get encryption key count value, if we can predict it, what happens when calling RTL random multiple times, if it changes the internal state of the vector, and also the return value of the query system time. So the encryption key count value is always initialized at 0 at system boot time. It is only updated by the get encryption key function, but as Hernan previously said, it is not usually called. So we can predict that that counter will be 0 if we start an attack. Also, calls to RTL random may change the internal state of the vector, but that's not an issue because we can know if that happened, so we could relaunch the attack again. So the consequences of RTL random can be circumvented. And finally, what will be the time when the get encryption function is called? Well, we know that based on the plot, that could be the same among consecutive packets. Only the middle 16-bit, probably the most volatile part of that value, is used. But we also found that the current system time of the server is sent to the attacker during the SMB negotiation. So the current system time can be predicted or known by the attacker. So knowing those factors, we built an attack. We designed an attack in 4 steps. First, to set that internal vector of the RTL random in the server to a known state, then calculate all the possible challenges that can be generated by that internal state, collect the possible responses, forcing a victim to respond to all those challenges, and then connect and use a valid response because the server will send a pre-calculated challenge. So the first step, we will request authentication as an attacker to the victim. The victim, once the authentication is requested, will call the get encryption function and will call the RTL random function 3 times and will update its internal vector. So, and will return a challenge to the attacker and also the timestamp in the packets. So what the attacker can do is simulate the store behavior of the M&M And then, well, loop to A until all the simulated vector is complete. In this way, we have a simulated state of the server. So once we have that internal state, we can go to the next step on calculate all the possible challenges that can be generated with that internal state. So the simplest way is to get the combination of all those values, but we can also try to guess which values are going to be issued also, but the simplest way is to combine all the values. Then how to collect all the responses for those challenges? Well, we could send an email to a victim with, for example, an HTML with image tags, and the victim will connect to the custom SMB server, and the attacker will send all the challenges pre-calculated using that internal vector, and the victim will send back the responses for all those challenges. And then the final step is to connect to the victim and wait for one of those predicted challenges in step 2, and respond with an informed response, a valid response, to the victim, and the victim will authenticate the attacker.
All right. I know that's like a lot of information, but the basic idea is that based on the fact that the server, based on the fact of how the function that is generating the challenges work, and the choice of the PRNG the function is using, and also because the server is basically leaking the seed, that is the current system time, to the attacker, we can pretty much simulate and do the same calculations that the server does, and we will basically replicate the internal state of the PRNG in our machine. So basically you have a remote machine, and we have our local machine, and we are going to know at any point in time what is the internal state of the PRNG used by NTLM in the remote machine when we want. So basically that can be used to predict all the pseudo-random numbers that the server is going to generate. And that allows us to do the prediction attack. The prediction attack is basically saying, hey, I know when you're going to predict this certain challenge, just this one, and I'm going to tell the client, hey, give me the corresponding response for this nonce or challenge, and I know that I can use that to authenticate against that server or any other server. So basically you are optimizing the attack and reducing the number of connections that you need from the client. And it's also, I think, once you have the time to understand everything, it's quite interesting in on itself from a technical standpoint. At least I believe that. So some very quick clarifications that we want to make about the vulnerability is that because of the way that we are actually getting the responses that we need from the victim or the victim in this case, some people think that this is some kind of SMB relay or SMB credential reflection attack, but it has nothing to do with that. It's actually, I would say, worse than that, because these flaws are breaking like the rules the protocol has to comply with. That is, that the nonce had to have certain properties. So it's kind of fundamental. It's like this is the thing that cannot be failing in this protocol, and it was failing. And also the patch that was recently published